Okay. Okay, all right. All right, so what should we do today? So today we have, I mean, I could start on something new, but you know, I think everyone would rather we do a little bit of a review for the midterm. And then my apologies for this isn't uploaded to the website yet. The website's being finicky. Again, for some reason, GitHub, the old add-ons for Jekyll that I was using are no longer supported, and and GitHub is starting to have a problem with it. So I'm going to fix that hopefully over the break. Oh, to be old and realize all the libraries that you learned to use are now deprecated. Very sad state. But I mean, that might be a benefit. That might be a beneficial thing because you know we could all be present, looking at the questions in the review on the lecture. So today we're just going to go over some sample questions. I posted the sample midterm, on the website on Tuesday, and the skill set. So the midterm will cover everything up to and including the lecture last time, Tuesday's lecture. So, you know, and on the homeworks, of course. So it shouldn't be too difficult. I really don't want to make this midterm difficult. I just want to ensure, you know, everyone's kept up and, you know, kept up with the homework, kept up with the lectures, that sort of thing. Honestly, I have no problem giving everyone A's if everyone actually, like, you know, came to every lecture and absorbed the material. Like, there's no reason why not. But, you know, we have to go through this song and dance because we don't hold exams, then of course none of us would like do the class, right? We would just sort of focus on other priorities, you know. So exams, homeworks, and all of these are just commitment devices. That's how I view them. So really, all I want is for us to have a basic understanding of the material, and then we would have learned something and we could move on. So today's lecture is just, we're just going to go over a couple sample questions that are different than the sample that I posted online. And then, so that sample, so between today's lecture and the sample online, you have two sample sets of questions. You'll have the homeworks and you have the lectures. So plenty of material, it's plenty of sample questions, plenty of sample midterm stuff to go over and prepare you for the actual thing on Tuesday. Sound good? So we're going to focus more, at least in this particular slide deck, I focus a bit more on the earlier stuff simply because, you know, it's farther away. So, you know, the stuff on torch.nn data set, the optimizers, hopefully that's very fresh in your mind. And you don't need too much recapping. There we go. Too much recapping on that. We'll just focus more on the stuff we did in the beginning of the course. So if we remember in the beginning of the course, we started out with tensors. You know, tensors, storage, memory, how tensors are stored in memory, how they're sliced, all that good stuff. If you remember strides, that you know you could copy a tensor and either you could slice it up, and depending on how you slice it, you could either allocate a whole new piece of data to it, or you could reallocate, you could change around the indexing scheme so that you don't have to reallocate any new memory. You just change around sort of the strides and size of each dimension to get what you want, right? So that's what we'll do today. So that's the idea behind creating a view of a tensor. And there are other important factors that we had to consider. For instance, the major one was operators with the underscore next to them. imply a in-place operation and do not allocate new memory. That's a pretty big one. That's especially important, for instance, when we're doing gradients, right? When we were doing gradient descent and wanting to calculate the gradients of a parameter with respect to the loss function. If we said, for instance, WGD equals WGD times, step size times gradient, that's bad, right? Because it reallocates a new tensor, and it reallocates a new tensor and assigns WGD to be a new tensor that doesn't have required gradient equal to true, right? So these in-place operations are essential because we want to maintain the properties of the tensor. We don't want to reallocate a tensor every time we go through a training loop, right? So that's why the in-place operations exist in PyTorch, to allow us to sort of define a model, be able to do operations on parameters without having to reallocate the tensor. And of course, again, I said tensor views could share the same memory, tensor arrays, and of course, we talked about tensor/array slicing as an efficient way to collect and index variables. Pretty much anything that you could do with NumPy, you could do with Torch, barring a few edge cases. But most of the slicing ideas with tensors, with the Torch library, are taken from NumPy directly. Okay, so pretty much anything that you've done previously with NumPy. Same thing with Torch. And of course, you could use Boolean operators as truth arrays to separate elements based on a condition. And so let's go to that. Let's try to find examples of that. And on the exam, I'm going to mostly focus on, well, actually, I'm not going to. I haven't decided that yet. Okay, I'll leave that thought. But let's have a particular. Let's see a particular data point. So we have this. We have this we have this code segment. And so, what do we want to know? We want to know, does B share the same pointer as tensor A? Does tensor B share the same pointer as tensor A? What is tensor A, by the way? Let's just start off with that. What's the shape of tensor A? Oh, please tell me. Yeah, a 3 by 2 tensor is 0. So how many rows is it? Is it 3 or 2? 3, yeah. So 3 rows, 2 columns, all zeros. Okay, so that's A. So B is equal to A dot cosine underscore dot cosine underscore. So what do we think? Does B share the same data point? Does B share the same pointer as A? Does B and A share the same? Yeah. Does B and A share the same data pointer? We knew with tensors that a tensor itself is a struct, right? A tensor itself is a struct that contains basically a lot of information about the tensor. It contains a lot of attributes. So for instance, required gradient is one of the attributes a tensor could have. Usually it's set by default to no. The stride or size of each dimension also attributes in the tensor that allows you to adjust. That allows you to slice the tensor without allocating new memory. And arguably the most important attribute in a tensor is the data pointer, which is specifically a pointer to a physical block of data, a physical block of memory in your computer, right? And so depending on what we do, either PyTorch will choose to keep the data pointer the same and just change around the attributes to create the new tensor, or it'll change the data pointer, basically allocate a new block of data, and then the address of that new block of data becomes the pointer to becomes the new tensor's data pointer. So, sorry, that was a bit of a tangent, but does B share the same pointer as A? Show of hands. Who thinks B does share the same pointer as A? Okay, nearly everyone. Does anyone think B does not share the same pointer as A? No? Okay, well, let's test it out. So we have our little helper function as usual, and I should go back and run this. There we go. And so if we run this, we are simply asking if the A data pointer is equal to the B data pointer. And what's nice about this equality is that it's overloaded. So even if there is a offset, it'll still give you truth or false. And it gives you a true. And of course, type storage is deprecated. Everything I use is deprecated. So type storage is deprecated. And so, yeah, they do share the same data pointer. Good, 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 good. I'm happy about that. So does C share the same data? Does C share the same data pointer as B? Show of hands. Who thinks C does share the same data pointer as B? Who does not think it should see? Okay, nearly everyone. Why not? Yeah, please, Ben. You are right, although I'm trying to think of a counterexample because I think there is a counterexample to this, but I'm not sure. Actually, no, you're not. Yeah, I think you're right. Yeah, let's go with that. Yeah, I can't think of an example where the add operator would cause if you use add, it would leave the thing in place. Okay, yeah, you're good. Yeah, so if we do our little helper function, we don't need to define it again. So they're not the same pointer. So the way I would phrase this, and I don't think your explanation is necessarily wrong. But the way I would sort of phrase this is that C has different data values to A and B, right? The C is pretty much just multiplying. C is pretty much just adding A and B together. So C does not contain the same data as A, and C does not contain the same data as B. It's just totally new data. So because of that, you have to allocate new memory because it is new memory. It is a new thing, all right? But yeah, but I think you could go with that rule that if you're using the add operation and you're not doing anything in place, then it's almost like you'll never have the same data pointer as well. I'm trying to think if there is a. There is a dot sum you could use with underscore. Well, yeah, there is if it's a scalar, if you add in like a scalar or something. That's what I'm thinking. So if you add a scalar, but yeah, you would have to do the in-place operation. Yeah, this is a good question. I'm going to have to think about this a bit more. But I think Ben is right. I'm pretty sure Ben is right. That's the hard thing about these libraries is that there's always a counterexample with Python. Oh man, I feel like my voice is too loud. Okay, all right. Hopefully that helps. Okay, good. So C and B do not share the same data pointer, mainly because the actual data values in C are going to be different than A and B, and we don't want to necessarily destroy the data in A and B yet because we might need it later on, right? Who knows? PyTorch is a scripting language, so you have to be able to keep these so you could reassign them, so you could process them on the fly. Okay, so what would we be printed if we printed each of A, B, and C? Who wants to try this? It's going to require me to zoom out a bit, but it's okay. Basically, we're just asking what the values of A, B, and C are going to be. I could tell you right now, print it. If we say print a bunch of tensors, it'll just say tensor, like print the actual tensor values, tensor, print the actual tensor values, and so on. So really the question is, what are going to be the values of A, B, and C? Yeah, please. Okay.
And then C would be like a 3 by 2 of all ones.
Okay. So A is a 3 by 2 all zeros. B is 3 by 2 of all ones, and C is 3 by 2 of 1 plus zeros. Right. So, what do we think? Happy with this or no? No, Dominic, please.
So because A and B are like B and B of A, they're both going to the same data. So when you take the cosine of the 3 by 2 of all zeros, you're overwriting that memory. So A and B will both be 3 by 2s of all ones, and C will be a 3 by 2 of 2s.
Yeah. So there is a hint actually in the previous parts of the problem is that A and B are I mean, B is A, right? So they can't be different. But the idea is that A dot cosine, when you do an in-place operation, that's literally what you're doing. You're doing the operation on the memory of that data. So even if you didn't have B equals there, if you just said A dot cosine stuff, it would still change everything to all ones still, right? So because of that, you have A is equal to 3 by 2 of all ones, B is equal to 3 by 2 of all ones, and C, what do we think? Would it be ones? Twos? Yeah, it'll be all twos. So we could just check ourselves. Come on. We could check ourselves and see, in fact, yep, A, B, and C are all, A and B are all ones, C is all twos. Okay? There's going to be a question like this there's going to be a very similar question to this on the exam. It's going to be a trap. Don't fall for it. Good? Okay. What else do we want to do? All right. Oops. Zoom out. Oof. Okay. So let's consider a code snippet below that creates a 10 by 10 tensor of random integers between negative 99 and positive 99. Makes sense. And actually, let me run that just to make sure we have it. Yep, there we go. So 10 by 10 tensor between negative 99 and positive 99. And then we would like D to contain the top right quadrant of A. So top right, so these values here. What should we basically change this expression to accomplish this? And in fact, I am going to, there we go. I'm going to say D is equal to A something. So how should we slice this? How should we slice A up to get the top right quadrant of the top? How should we slice A up? Yeah, to get its top right quadrant. Yes, please, Dominic.
It would be something like in the first one would be like 5 to 10, I think. I forget if slicing is good or not, but we would say 0, 1, 2, 3, 4. Yeah, I think you'd have to do 5 to 10 because I don't think the edge one is inclusive.
You would have to do, yes. So you would have to do, let's do it. 5 to 10, 5 to 10.
Well, 5 to 10 and then 0 to 5 maybe?
5 to 10, 0 to 5. Let's see. 0 to 5. Let's just print that. Let's see, what do we get? We get 86 to 25, so we get this one. We get this quadrant. What happened? Dominic, fix it. I know you could.
Oh, yeah, I flipped it.
Yeah. It's 0 to, yeah, I do that all the time too. But you're right. I mean, your fundamental question, does the 5 get included? And that's, yeah, it doesn't get included. Of course, with A range, yeah.
We need to switch to 5 to 10 then also.
Switch the other one to 5 to 10? Oh, top right, yes. Top right. I was thinking top left. Yes. There we go. Sorry. Yeah. Easy peasy. What if, man, these, what if we didn't know what if we knew it was two-dimensional, but we didn't know the size of each dimension, but we still wanted the top right quadrant of A? So basically, I don't want to include these numbers, like actual numbers. I want to basically make it more generalizable, so that if A was a like 42 by 23, 42 by I don't know, something even. 52, 42 by 52 matrix. We could still get the top right quadrant with the same expression. How would we do that? Yeah, please, Patrick.
Well, instead of, first of all, instead of putting 5, you could put a dot shape,
Yeah.
like a 0 or 1, which gives you a halfway.
Yeah. Yeah. So A dot shape. Let's say 0 over 2, and then a good thing to do is this will definitely give you an error. Well, we could try it. I could show you guys. So this gives you an error because this will return, the divide by 2 returns a float. So we could just do int. So that still works. Is that correct? Yeah. Oh, sorry. I had a weird premonition. So yeah, we could just use A dot shape. That's the major thing. Okay, good. Come on. So let's say we want H to contain all the multiples of 4 in the third column of A. Exciting. What should F, G, and I be to accomplish that? So, actually, I'll make a new code cell below. I'll copy this so we could experiment. And then, oops, well, of course that didn't work. Print, nope, not print E, print H. Okay, so, I mean, we don't have to stick to this format very firmly, but it's probably not a bad thing to do that. So, how should we get only the values that are divisible by 4, and by third column we are keeping it to this. And actually, do we have any values divisible by 4? Well, in this case, we'll just say the third column is the column number 3. We'll just, and in fact, I'll just change that. We would like to in column 3. In column 3. There we go. Good. That improves it. Yes. Okay. So, what do we think? How do we accomplish this? Yeah, please.
I think F should be like just a colon, right? Not the entire, in every row.
Okay.
And then G should be, okay, so, sorry, column 3, so like
This?
next 3. Well, yeah, that depends. Is it like, is it column 0, 1, 2, 3, or?
Yeah. Column 0, 1, 2, 3.
So yeah, I'll leave 3, and then I haven't gotten to H yet.
Okay. Let's see. Let's just see if that first part works. Let's see. Is this column 3? Yes. Yes, this is column 3. Also, there is no multiples of 4, is there here? Nope. Here, let's just regenerate this real quick. Damn you.
You got 60.
I got 60. Yes. Okay. Good. Good call. Okay. So we got a divisible by 4. So we should at least get negative 60. All right. So how do we get only negative 60? Oh, come on. Tommy.
If you like for I in range of E dot shape, and then your condition will be, maybe not for I in, but I guess maybe. But like something where you kind of loop through all of them, and then the condition will be, E at I, or
And then, wait, so we're, okay, say that, go on.
You gotta loop through all of them, and then inside of looping through all of them, you'll just check if that number is divisible by 4. So mod 4 equals 0.
Okay, so let me see. I'm gonna keep this here. I'm gonna keep this here. I'm gonna, or E something, whatever. Something. So you're saying just have a for loop for I in range, len E, then if EI modulus 4 is equal to 0, what, H dot append, maybe?
Yeah.
EI, nope, EI, yes, that.
Yeah.
Okay, and we gotta initialize H to be something empty. All right, let's see. Yeah, seems to work. Seems to work. I will give you this. It does work. And honestly, if you put this on the exam, I won't mark it wrong. It's correct. I'm not one of those people that's like, oh, your code has to all be, like, I'm not like one of those Pythoners that's like, everything has to be done in a single line. It's a little absurd. There's a simpler solution, though. Does anyone? Yeah, please, Ben. Yeah.
So in the bracket themselves, should we have to do like a modulus 4 equals 0 on this?
Okay, in here or in here?
Yeah,
Okay.
my instinct is that we should just be able to do E and then in the bracket put the statement. And
Okay.
I'm kind of hoping that the
E.
syntax allows us to automatically infer.
Like this?
Yeah, because wouldn't that do, it takes E and then it would return a bunch of true and false, and then that list of true and false would like be used as the.
Oh, beautiful. Oh, beautiful. Okay, so we do that. That does increase, and your explanation is dead on. So let me break this down into a little bit of two parts, so we could view exactly what's going on. There you go. You do EI, and then so if we print EI, oh come on. There we go. What does it do when we have this expression on a vector? It gives you a new vector of true and falses. So as we'll notice, it gives you false, false, true. This corresponds to false, not divisible by 4, not divisible by 4, divisible by 4, and the rest are, I guess, not divisible by 4. And then you just put those vector true and falses in there, and then everything just sort of works out. And then the true and falses basically means I want this element, I don't want this element. I want this element, I don't want this element. And so when you do all that, you get a vector of only the indices that were true. Like that. Yeah, that's a very Python specific thing. But it is beautifully compact. So I guess that's one of the reasons people like, again, one of the reasons people like Python, because there are tricks like this that make things sort of beautiful. Yeah, please, Daniel.
Just a quick question. When you're doing size vector D, is it 1D since there was like 1D vector versus 2D
So you're saying because A is 2D, why isn't E 2D? Or?
Yes. Like is E 2D or 1?
Oh, E is one-dimensional, right? So we could see that here. Yeah, E is one-dimensional, but I do see what you're saying, that it feels like A is A is two-dimensional. So at the very least, like E should also be two-dimensional, even though this dimension or this dimension will just reduce to 1, right? It will be a size of 1. Python takes care of that. Sort of, I think it's implicit in when you do slicing that it basically runs sort of a squeeze that gets rid of the dimensions of size 1. And actually, I mean, that's what's, remember that the squeeze function gets rid of dimensions of size 1. The unsqueeze function lets you add in a dimension of size 1 somewhere else somewhere in the matrix in the tensor, right? That was a kind of a, I don't think that's specific to Torch, but it is used a lot in Torch, I should say. Yeah, makes sense? Is all this coming back to everyone? All right, so linear algebra. Linear algebra, we have a bunch of stuff. So linear algebra was mostly devoted to matrix calculus. Well, we talked about solving systems of linear equations with PyTorch. That was pretty self-explanatory, and I don't think I'm going to test you guys on how to solve a system of linear equations with PyTorch, because I mean it's trivial. So that homework problem is probably staying in the homework. But again, we talked about how we could represent vectors of functions and basically take the derivative of vectors of functions with respect to another vector. So a lot of the linear algebra part of the course, part of the lecture, was on matrix calculus, right? So there will be at least one matrix calculus question on the exam. Study the examples from the sample, from lecture, from homework, and I think you'll be pleasantly happy with what you see on the exam. But let's go through an example. Let's go through a sample problem. And actually, I'm going to jump onto my iPad. I am going to jump onto my iPad. And I got it. No, why are you doing that? On Notability. Where's Notability? Right there. Perfect. Okay. Oh, why isn't this working? Okay. And let's there we go. There we go. All right, so the problem. This is a sample linear sample vector what is it? Matrix calculus problem let's go through is compute the derivative of the partial derivative of f with respect to x, where oh, there we go. F of x is equal to 1/2 ax squared. Squared means squared, and x is a vector. Yep, is a vector of size n, and A is a matrix of size n times m. M. Yes. Okay. Okay. Does that make sense? So we want to, so it's ax 1/2 ax squared, and we want to take the partial derivative with respect to x, where x is a vector, a is a matrix, and so the function f of x is 1/2 ax squared. Yep, that all makes sense. Any questions here? Yes, please.
And then what the subscript is.
Oh, perfect. That's what I was going to just ask. So literally, the subset of 2 is the mean square distance. I think mean square distance, if I'm remembering the term right. So literally, when you have a matrix, or if you have a vector, I should say, if you have a vector, and I want to write this as A is a vector, of size, of size n, A is a vector of size n, then this would be equal to the absolute value. Well, you don't need the absolute value, but this is equal to the square root of the sum of I equals 0 to n minus 1 of a squared, of ai squared. Okay? So basically, it's literally calculating the magnitude of the vector. That's all that means. So all this means is you're calculating the size of the vector, and then this term right here is literally superscripts. So what this does is that you're basically getting rid of the square root. Okay? So this you'll see a lot in, I mean, this is literally the loss function here, right? That's why you see this a lot in machine learning. But you have to get rid of the square root, which is why the 2 is here. But this whole thing is the vector magnitude. So that's all that means. Make sense? Okay. I wanted to be sure I introduced it because I don't know if I use it in the lectures. I don't remember using it in the lectures, but it is very common in books and stuff. So I wanted to make sure you guys knew what that was. Okay. So knowing that, literally all this is just basically the double, basically this is AX transpose times AX, right? So that's all that amounts to. So how do we handle the derivative in this case? What is the shape of the derivative going to be? Oh, please. Oh, sorry. Question. Yes. Say that again?
So it's a times x, then you're talking about n by m matrix is a n by 1 vector.
Yeah. So it's going to be a vector size m. This is just an example. This is separate. This is a separate. Oh, the shapes won't work well.
The inside shapes have to match.
Oh, well, I mean, I see what you're saying. Yeah. Okay, let's do that. Let's just make sure. 1 by n. Does that work?
I think he was saying m by 1.
M by.
Yeah, because you have n times m times m by 1, but the m and the n don't match.
So you have. Oh, did I do this wrong? Wait, I have n indices. Wait, oh. I have x. So this is n. This is n length. And then I have a matrix that is. Oh, I see. Oh. Yes. Okay, got it. Okay, so it should be, or it should be m times n, right? well, there's a couple different ways to do this. Let's keep it like this. Then we could just m times n, right? Does that work? Yes. Yes, okay. Okay, sorry about that. Yeah, you're right. You're right. Oh, man. Matrix math, man. Okay, so, so that makes sense. Okay, thank you guys for correcting that. And get rid of this. So, what should we do in this case? Any thoughts on how to handle this problem? You know, we could simplify this a bit. We need to calculate df dx, but we haven't seen this before, ax, but what if, I ruined that, what if we say y is equal to a times x? Then we could say f of x is equal to 1/2 y squared. So this is just like 1/2 y transpose y. Yeah, that makes sense. But then what does df dx equal? Oh yeah, you absolutely have chain rule in matrix calculus. Yeah.
And therefore, then the derivative of y transpose equals to the transpose of derivative of y, right? Like, then with the transpose is linear, it's a linear derivation, right?
Right. Yeah. Yeah.
Then because we know y derivative is just a.
So what? So okay. So you're a couple steps ahead of me, but you're not wrong. So what would df dx is equal to? Since we have chain rule, how?
We would have derivative of y transpose times y plus y transpose times derivative of y
You would have the derivative of y transpose times y.
plus derivative plus y transpose times derivative of y. Product rule.
Yeah.
Whatever.
Yeah. Chain rule, right? Yeah. 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 So okay. So I think you guys are right, but I just want to write this explicitly. So df dx would simply be equal to df dy times dy dx, right? So I know that's really, you guys already got that, but I want to write that explicitly. And so in this case, what is df dy? And you said it multiple times, right? You said, yeah, 1/2 y transpose, because this multiplied times y. I mean, it's literally like normal calculus, y transpose. Then what is dy dx? dy dx. dy dx, y is equal to ax. So dax times the derivative of x. What's that equal to? A, yeah. A. So yeah, that makes sense. And then we could write, so the df dx is equal to 1/2 y transpose, which is simply ax transpose times a. And if you stop here, that's absolutely correct. It's absolutely correct. But if you, for instance, another way to write this is taking the transpose of all, if you take the transpose of df dx, you would get the transpose of this. And so 1/2 comes out of there. You would have to reverse the matrices. So you would get A transpose AX, right? And typically with matrix calculus, you don't necessarily care if you get df dx or df dx transpose. You could write it either way. People usually call it, people usually accept it either way. Because it really depends on even that value there. It depends on how you define the dimensions. So yeah, does that make sense? So not too hard. Don't forget the chain rule. But again, one of the things that you just should be careful of is, I mean, it's just matrix calculation, matrix calculus. I'm just going to ask you a very simple matrix calculus question and your reasoning behind it. So please give some reasoning behind it. You have to give some reasoning behind it, okay? I know even though the solution will be obvious, just make sure you're able to understand the logic behind it. What else? What else do I want to? Well, maybe I'll give you a different. Do I want to do that? I'll write out because I don't want to spend all day on it. I want to get to the compensation graph question. But another way to compute the partial derivative is simply to say f(x) is equal to 1/2 ax squared. This is equal to 1/2 ax transpose ax. We said that. So now df dx is equal to 1/2 d ax transpose dx just the derivative of this. Ax plus ax transpose dax dx. So we do the product rule, right? Product rule still works in matrix calculus. And then we do 1/2. We just simplify it a bit. So we reverse these two. We reverse the order of these two by using that transpose property. We simply say dax dx tax is equal to, we reverse these two by saying plus dax dx transpose ax I caught myself. We made a mistake, but we'll come back to it. Dx is equal to well, it's both derivatives transposed because we're reversing the order of operations here. So it works out to be the same thing. X transpose like A transpose B. A transpose times B is equivalent to B transpose times A. So that's like a neat little matrix identity. And then you simply say that's why. Okay. We simply don't need to we bring this out of the parentheses, and we simply say this gets negated because we have two of this term, and dax dx transpose ax is equal to this, and then this equals A transpose ax. Okay, so we're missing 1/2. I will tell you that this solution is correct. This solution is correct. I missed the error last time. But but the 1/2 shouldn't be here. Where did we make the mistake? Does anyone know? Yeah, please.
The FDY should be
Yeah.
YT.
Yeah. I wasn't paying attention, but yes, the FDY right here. This is equivalent to this. Another way to think about this is 1/2 x squared, right? So the derivative of this, you would have to carry out the 2 and cancel this out. So df dy should just be equal to y transpose, and then you would get rid of that 1/2. That threw me. I wasn't paying attention enough. Oh, shame on me. Yeah, but hopefully that makes sense. We learn more from our errors, right? Okay. And if you do out, I encourage you just do out the summation of this. Just do out the summation of this term, and then you'll see why that is. Make sense? Okay. So, last thing, we're running short on time. So, I want to get to a computation graph question. And in fact, let me jump quickly back and forth. Come on. There we go. There we go. So if we remember, computation graphs were incredibly important for calculating gradients, right, of complex functions. So we have this thing called backpropagation, and it works by basically, for every step, we calculate the gradients and then multiply it by a particular learning rate, and then adjusting the step size. So the important thing to note is that a lot of our earlier functions, we calculated the gradient directly using the chain rule, right? So remember the chain rule, it's very important. So it's very important. There will be a question on calculating the gradient for a complex example where you'll have to use the chain rule on the exam. So that is important, calculating a gradient directly. But the other thing is that we talked about is that occasionally we don't necessarily want to always have to calculate the gradient by hand. We maybe, a lot of times, the actual function, the objective function, will be super complex, right? It'll be something like this, right? So calculating a gradient by hand, while not impossible, it's just very tedious. So that's where computation graphs come into play, right? So we had a computation graph question, and we had a computation graph example in lecture. You guys did a computation graph example in homework. There's another example in the sample midterm. And let's go through a computation example right now. So what we want to do with this computation graph is simply to be able to calculate the gradients. But before we can calculate the gradients, we need to be able to represent the graph. We need to be able to represent the function using the graph, right? So I didn't include the values of each node. The idea behind the first thing we could do is what could we do? Well, the first thing we could do, we could hand calculate the partial derivative. Yeah, we can start off with that, hand calculating a partial derivative. Then we'll try to calculate the partial derivative using computation graphs, and hopefully that will close out our discussion. Okay, so let's go back to the iPad real quick. Let's go back to the iPad, and I want you. Okay, so first thing, calculates, ooh, I'm not a big fan of the bright blue. No, let's just keep it black. Calculates df dx and df dy. And in fact, I will copy this down. Copy to keep everything on one screen. Come on. Copy. Paste. There we go. So, I think a lot of you are already ahead of me. What is df dx? Anyone want to just wing it? You guys just chain rule it, basically. But I don't think this one is too bad to just sort of, you don't need to write down too many intermediate steps for this particular one. Anyone? Yeah, please, Patrick. Yeah. For cosine xy, oh, xy, yes, times negative sine of xy, good, times y, yes, yep, and then plus
negative y negative sine xy over cosine xy.
y, okay, so yeah, I put that negative there. Oh, actually, let me, maybe to keep our sanity. Y times negative sine xy over what?
Over cosine xy.
Cosine xy. Yep. Yep. Pretty much bang on. And just to reorganize this a little bit, negative 4 cosine xy sine of xy, negative 4y of xy, yep, plus or minus y sine xy over cosine xy. All right, just cleaned up a bit. All right, who wants to do df dy? Very similar. Daniel, you know that?
Yeah, there's just
Yeah, negative 4x cosine xy sine xy minus x. Yeah. Y over cosine xy. Okay, brilliant. All right, you guys got this. Okay, so we've established we've established you really know the chain rule. Fantastic. All right, so let me copy this a little lower. Copy. Can we do this? Yes. Can we do this? Paste. Yes. Oh, thank you, Notability. All right. So right now, and let me, oh, well, maybe I can move this in closer. Yeah. There we go. Okay. So we want this computation graph specifically to represent this function. Okay? Now, in reality, there are multiple computational graphs that could represent the same function. So I won't be, so, you know, is this fair? Yes and no. I mean, the question, the question is more about how do we fit a function to a computation graph. But I will cede that there are multiple different computation graphs that could fit to a particular function. Okay? That being said, this is a fun little exercise to try to get a particular computation graph working. And I could tell you there is a set of values that will be able to represent this function using this computation graph, right? So we want to assign W1, W2, W3, W4. We want to assign functions to W1, W2, W3, W4, W5, W5, W6, W7, and W8. W8. Huh. Such that this computation graph here will represent this function, okay? So it's basically like a fill-in-the-blank challenge. Fill in the functions for each of the W's to get a particular computation graph going. So let's actually, I'm going to fill it out on the graph itself. I mean, I can do that, right? Yep. And I'll do it in, yeah, I'll do it in black, this forward pass. So what should the values of W1, W2, W3, W4, all the rest of them be? What should those functions be in order to get the f of x to match the f of x we desire? Does anyone want to give it a shot? Yeah, Ben. Why not?
W1 will be x.
Okay.
Going to W3, and then W2 will be y going to W3.
Yep.
W3 will send W1 to W2.
Yep.
W4. From W4 to W5 should be cosine of W3. And then,
Yep.
or cosine W3, and then cosine W3 will also be on the arrow going from W4 to W7.
Okay.
And then from W7 to W8, it'll be ln of W6, or sorry, ln of, I did it wrong once, ln of W4, or W7.
For W5 or W7? Wait.
From W7 to W8,
Yep.
it should be ln of W7.
Oh, okay. ln of W7.
And
That's
then
good.
W5 to W6, it'll be W5 squared. And then W6 to W8, it'll be 2 times W6.
And then 2 times W6.
And the final one will be W6 plus W7, the arrow.
Yep. Yep. Bang on the money. All right, I have no complaints. Does anyone else have complaints? No? Everyone happy with that? All right, good. So the forward pass, this seems to work, because if we go through the forward pass, then we have, and I'm going to write this in green. If we go the forward pass, or blue, fine. Yeah, blue. This W3 would output xy. W4 would output cosine of xy. At W5, the output would be cosine squared xy. At W7, the output would be natural log cosine of xy. And then at the output of W6 would be 2 times the cosine squared of xy. And then at the output of W8 would be 2 cosine of xy, cosine squared of xy plus natural log of cosine of xy, which is what we wanted, right? That matches, that matches. We're all happy, right? Okay, so what do we do now? We want, let me get rid of these notes. It's going to get very crowded in a second. So now we want to calculate the partial derivatives. We want to calculate the partial derivative of df with respect to dw8. We want to calculate the partial, so that's this way. And then we want to calculate the partial derivative of dw7 with respect to dw8 with dw8 with respect to dw8 with respect to dw7, w8, yes, dw7. Is this going correctly? Yep, okay, yep. And then we want to so on calculate the partial derivative of dw7 with respect to w4. This is dw8 with respect to w6, and so on. Right? So let's just fill out those partial derivatives. Let's fill out the partial derivatives, and let's just fill it out on the graph itself, because why not? It'll make things more visually interesting. So, what's the partial derivative? df dw8. What's the partial derivative here? Yep, 1. Good. 1. What's the partial derivative from dw8 dw6? Derivative with respect to w6. Yeah. It's just the derivative of w8 with respect to w6 is 1. Derivative of w8 with respect, because w8 is this function, don't get confused. w8 is this function, and so the derivative of this function with respect to w6 is 1. Good. The derivative of w8 with respect to w7, 1. Good. The derivative of w8, we're going from here, the derivative of w6 with respect to w6 with respect to w5? Yes, yeah, okay, just making sure. The derivative of w6 with respect to w5? Two, yep. The derivative of w6 with respect to am I? Yeah, yeah. One sec, let me see. I might have a mistake in my notes. w6 equals 2w5. w6 equals 2w5. Yes, there we go. Why did I put w6 equals 2w5 here? Yeah. w5. Yeah, that's it. Okay. I was wondering about that. Yeah, I was like, why is w6 there? Okay. And w5 squared, I think w5, this should be w4. That's where I went wrong. There we go. God. Okay. Okay. So, the derivative of w6 with respect to w5 is, of course, 2. Does that make sense to everyone? All right. Okay. Yeah. Thank you. Sorry about that. Okay. So, respect of w7 with respect to w4, what is that equal to? Yeah, 1 over w4. w7 with respect to w4, yep, 1 over w4. The derivative of w5 with respect to w4, 2w4, I heard it, yep. And then the derivative of w4 with respect to w3, what's that? Yeah, negative sign w3. ln of w, yes, yes, thank you, yeah. I lost my mind somewhere around there and started and lost count. Thank you, yeah. And then w3, the derivative of w3 with respect to w1, what's that equal to? w2, exactly. w2, derivative of w3 with respect to w2, w1. Okay, perfect. All right. So we calculated the partial derivatives for each node, for each successor node. Okay, so that's simply the reverse location, and so now we need to calculate the adjoints. Okay, basically the running derivative. Okay, so the derivative of w8 with respect, the derivative of f with respect to w8. Is what? 1, good. And let me put it in 3. So 1. And Say that again?
The notation for that's like W8 bar.
Yes, the notation is W8 bar. Yep, this is, I should put the notation here. This is what's called the adjoint, right? So W7 bar, yeah. W7 bar, what's that equal to? 1, yep. W5 bar, W6 bar is also equal to 1. W6 bar is equal to 1. And then I'm going to stop doing the W bars just for sake of time. So what's the W5 bar? 2, yep. What's W4 bar? Yep. So 1 over W4 plus, what was it? Yeah, plus 4. Was it 4W4? Yes. Okay, yep. Times 2. Yep. W4. 2W, so it's just 2 times 2. So if we just wrote it in parts, 4W4 and 1 over W4. That makes sense. And then so we got a total thing here. And then what's W bar 3? Now it gets tedious. It's just multiplied. It's just the multiplication of negative sign W3 times these. So negative sign W3 over negative sign W3 over W4. Negative sign W3 over W4. Yep, minus notability, yep. Minus 4W4 sine of W3. Is that correct? Yep. Oh man, these scam calls have gotten nuts. And then W2 bar is simply negative W1 sine, or W1 bar is equal to negative W2 times sine W3 over W4 minus 4W2 W4 sine of W3. Okay. And then, of course, x bar. Well, do we need to calculate x bar? Well, maybe we could. It's the same thing. Yeah, substitution. So, just to make sure, just for our sanity, let's get this and let's do the substitutions. Copy this somewhere here. There we go. Paste this. Ooh. Okay. So let's bring this down here. Let's just say down here. So what is W2 equal to? It's x times the sine of W3, which is xy. Yep. xy. Oh, should it be a y? Yeah. Yep. W2, yep, it should be a y. Yep. Thank you. Negative y over W4, which is, what is W4? It's negative sine. I should have left that up. Yeah, it's negative sine xy. No. W4 is equal to yeah, cosine xy. Yeah, why am I pausing? Yeah, cosine xy. Cosine xy, then minus 4 times W2, which is y, times W4, which is cosine xy, times times sine of xy. Sine of xy, this is df dx, or otherwise known as W1 bar. And so does this match what we had previously? Yeah. And we do the same thing for df dy. Okay, so everything works out. Okay? All right, so a little tedious, but hopefully that all made sense. I will post the rest of the lecture, but it wasn't. I didn't really have any more problems. It was just basically a recap of the stuff we have addressed so far. Gradient descent, backpropagation, linear regression, linear classification, and I think probably for the cheat sheet, I think I'm just going to include one sample of the torch.nn plus dataset code. I think that's all you need. I don't want to put too much stuff into the cheat sheet because then I got to make the problems more complex. If I don't put in a lot of identities and stuff in the cheat sheet, I could just test you on those identities, which would be nice, right? So I'm just going to put in like a sample piece of code for the cheat sheet, and so you could like know the syntax, but otherwise you shouldn't need any complex function. You shouldn't need to have any complex functions memorized and stuff like that. Okay, so hopefully that makes sense. I will see you guys on Tuesday. Have a good weekend. Homework 6 is still due Monday, and study for the midterm. And yeah, have a good weekend. Yeah, hey.
Hey, so when exactly is the midterm?
It's in lecture 12:30. Yeah.
All right.
Sure. Why dAx of with respect to x is equal to a?
Yeah, I thought it's a transpose.
Well, the function is just ax, right? Yeah, so if it's just ax, then the derivative of that function, it should be just a. I mean, the partial derivative with respect to x should be just a. It should be, it's like a is a constant in that case, right? Yeah.
Why for this expression, if I also use the chain rule and I regard this function as this one, and if I use a transpose, I follow this.
You get pretty much the same steps? Yeah.
Yeah.
Yeah. Yeah, I mean, so this is one of those things in matrix calculus you don't necessarily care about, like flipping the way we're using it, I should say. The way we're using a lot of matrix calculus, it's very loose, so you don't necessarily care if you flip the rows and columns a little bit. I mean, as long as sort of the dimensions are consistent, then it should give you the same result.
Oh, so this one is also correct.
Yeah, yeah.